So, good afternoon. Welcome to Krishna's classroom. Last time we concluded our lecture by defining what is called compactness. Now, let me just recall the definition. The definition was this: XD a metric space, A subset of X, A non-empty. We say that A is compact if every open cover A has a finite subcover. That means if A can be enclosed in, the union of what is called open sets, say alpha belonging to some index set, then there exists a finite subcollection of U alpha of say U alpha 1 such that some finite number k. Now, this is the definition of compactness. And the important part that you have to observe is that every open cover for A has a finite subcover. It should be true for every open cover. Okay. Now we have seen some examples, very fascinating examples. To just recall, because they give some insight into what exactly is compactness in some known metric spaces. For instance, we will start with R. Okay, so we start with X equal to R and then explore what are the compact sets. Now we have seen that we look at some examples. See, the best way to understand a concept is to explore the sets which do not satisfy them. For example, we have looked at this collection. Suppose A is this. Then we observe that union n equal to 1 to infinity contains is an open cover for A and has no finite subcover. So this particular set fails to be compact. That is, A is not compact. On the other hand, suppose you take A union, and 0 has a significance. 0 is the limit point of the set A. If you take B, then to cover 0, you have to introduce another open set. Okay, so something like, then to cover 0, we have to introduce another open set like minus epsilon to epsilon positive or some epsilon. Then no, this is rather, I think, n equal to, yeah. So, n equal to 1. So, n equal to 1 to infinity. One is an open cover P. Now you see that this is the scenario. You have 0, minus epsilon to plus epsilon, and you have the sequence 1, half, 1/3, etc. This is say 1 by. Now you see that as long as epsilon is positive, the tail of the sequence is contained in minus epsilon by epsilon. So you can drop it out. You can drop out the corresponding open intervals which is required to cover those points. Okay. Therefore, you can take a finitely many among from them and then adjoin to that minus epsilon to plus epsilon, so that will give a finite subcover. Therefore, it becomes, in this case at least, this particular cover has a finite subcover. In fact, you can show that this is compact. Okay. So that's the argument that you use. So one thing that you observe is that one of the shortcomings of the set that we started with is that it does not contain all its limit points. Okay, that 0 is a limit point which is not in A. So you see that then one to m minus 1 m the interval 1 by n union is a finite subcover. And one can actually show that I have shown that one open cover has a finite subcover, but it actually even implies even deeper. It says that it is, and one can show that B is compact. Because one can show that every open cover finite subcover. So you see that 0 is a limit point of A which does not belong to A. And this is one of the shortcomings. And that is, I mean, if you analyze it carefully, see that this is the problem that you have. Okay, we'll explore another example. Suppose, so another example, 2. So this is the first example. Right? Second example we recall is this. Suppose A is equal to the open interval 0, 1. Now you see that the intervals one, open cover for A, but it has no finite however, if you see 0 is a limit point. Zero is a limit point of A. So also the collection 0 to 1 minus 1 by n infinity is an open cover again with no finite subcover. However, if we adjoin two open sets to the cover, to the open covers, which contains one, then it gives an open cover for the closed bounded interval 0, 1, which has a finite subcover. So it appears this is compact. If not compact, but is. So this is the conclusion that we make. Again, both 0 and 1 are the limit points. We also observe that the collection 1 by n is not closed. So also closed. These are some of the observations that we make. So probably the reason could be this. So can you assert that all closed subsets of R are compact? Now if you try to make such an assumption, then you have the following example. So the question is, R compact? The answer is no. Consider minus infinity to plus infinity. Now If you take un equal to plus n belonging to n, un is an open cover but it has no finite subcover. Now you see that minus infinity to plus infinity is closed but not compact. Although it contains all its limit points, it's not compact. And with the usual metric, we are working with the usual metric. So what is the difference between the two types of examples that we have looked at? Observe that is bounded. So also but not closed. Now this collection also so we have R minus infinity to plus infinity is not bounded although it is closed. Not bounded although it is closed. So what we have done in all these situations is this. To take this one, this is not bounded and this is not closed. So this is bounded. So this is bounded but not closed. So put all these things but not put all these things together. You put all these things together, it looks a subset of both closed and bounded then it is compact. Now I'll put a question mark here. This is something that. So this is our speculation at this stage. Is this true? This is the question. This is the central question that we address. So you see, by examining different examples, you get some insight into the concept that we have introduced. Now what we want to say is, does it mean that it is the compactness is equivalent to closed and boundedness? Okay, that's our question. In R, now let us see what happens if you consider metric spaces, other metric spaces. So first we explore this problem in R and then try to prove it in the general metric spaces, if that is possible, wherever it is possible. So in this context, a partial answer at this stage is given by Heine-Borel theorem. Okay, so a partial answer to this question. The celebrated Heine-Borel theorem. So let us make the statement of the theorem. What does it say? It says that if you have any closed bounded interval, it is compact. That's the theorem that we are trying to prove. It's compact. So let us prove this theorem. We prove this by, see, if you look at this one, see that remark. Now we give the proof of this theorem. We assume that the result is false. Assume then we arrive at a contradiction. This is a broad strategy for proving the theorem. Okay. So let us take J AB. Now the strategy is divide into subintervals and their union is the J. Okay, then what you have is this their union is J. That is bisect. We bisect J. Let I belonging to some index set be an open cover for J. By assumption, which does not have a since J is assumed to be not compact, such an open cover exists. Not compact, such a cover exists. Such an open cover exists. Okay. Now what can you say? Then out of the two parts, one of them has A has no finite subcover. No finite subcover. So the whole J does not have a finite subcover. Let J1 this subinterval. Once again, you repeat this. So what is happening? This is what happens. You have this interval AB. So you have two intervals. Okay. Now either this one does not have, for which UI is a open cover, does not have a finite subcover, or this one does not have, or maybe both also. So if both are of that type, then you can choose one of them. Now let us work on this. So call that J1. J1 into 2 equal again, one of them has an open cover with no finite subcover. So continue. So call such an interval J2. So you subdivide. Suppose this is the interval on which UI is a cover but has no finite subcover. Then what you call this J1. So on J1 you further, and out of which one of them will not satisfy this property for compactness, and that you call J2. So what happens is that repeating this process, we obtain a nested sequence of intervals, sequence of closed bounded intervals Jk with not admitting a finite subcover. That is, each Jk has Ui as a open cover with no finite subcover. So we have J1 this. So if C belongs to, we show that there exists a C intersection AK then C belongs to alpha for some alpha. It's obvious. There's this to show that this reduces to a singleton point. See. And then it is containing some U alpha. And we now have Jk contained in U alpha for every k that means from K1. Therefore, what happens? If you take Ji I less than K1, then it has a finite subcover. Or you see that all the Jk's with K greater than K1 has a finite subcover, which is a contradiction. Which is a contradiction. Thus, we have so that is a strategy. But how do we have to work out the details? So let us examine one after another the steps that we have. What we have said is J is partitioned into the union of two closed subsets by bisecting it. And suppose both of them have the property that the open cover UI has a finite subcover. Then put them together, that becomes a finite subcover for the whole of J. Okay. Therefore, if J does not have, that is the open cover UI for J does not have a finite subcover, then one of them at least should be of the same type. Okay. So the first thing that we observe is that one of the partition, or what you call it, and open cover no if not J would have that's the argument. Because if this will have some U1, U2, etc., UK, and this will have some, say, another subcollection from it, say U alpha 1, U alpha 2, U alpha 3, etc., U alpha k, and here U beta 1, U beta 2, etc., U beta r. Then put them together, that will form a cover, open cover. That's the argument. Is with finite subcovers. which implies beta 1 so this and has and that's a contradiction. Therefore, our first statement that one of them will have no one of them will have this u alpha or ui as an open cover with no finite subcover stands, and this argument runs across. So all the JK will have this property. Okay. So let us AIBI. Okay. Then what we have is that J1 E1 and AI is less than or equal to A1. Sorry. A is less than or equal to 1. Then what we have is this. For J1, further, that is the first observation. Second observation is the following. Second observation is this. Length of J1 is equal to B minus A by 3 A. These are the observations that okay. Now we go to the repeating this argument. JK JK, we get the following problem. 1, with no finite sum. Second property is we have length of and third property is AK minus 1 AK. Therefore, what we have is a monotonically increasing sequence of points AK. That is, you have this is the sequence set. Now, this sequence AK belongs to AB for every K. That is, AK is bounded by B for every. This is what it is. So it's a bounded sequence. Therefore, it's a monotonically increasing sequence which is bounded above by B. That implies it's a convergent sequence. So let C denote the supremum of K, which in fact belongs to, so C belongs to A. Now this is how C is defined. C is defined as a supremo. Okay. Now what we do next? What we do next is the following. We in fact prove that the intersection of JK, because it's a nested sequence, consists of exactly one point C. Okay, so that's what we expect. So let us work on that. Now look at BK, the other end of JK. This is a decreasing sequence. Bounded below A. Therefore, that also converges. So this sequence also converges. Whereas D is the infimum of it. Show that C equal to D. Now we estimate this. This is less than or equal to C minus AK, AK minus BK, the triangular inequality repeated here. Now you can show that, okay, what about this? See, this can be made arbitrarily small by choosing k greater than, so AK such that epsilon by 3 for similarly there exists K2 Now, mod AK minus BK is equal to the power minus K mod B minus C. And choose K3 such that which exists. K3. So now you choose, hence for every we have mod C minus D is less than so since epsilon is arbitrary, C equal to D. So C is an element of AB, which implies there exists some U alpha, there exists some alpha such that this is an open set. So C is contained in that. C belonging to U. Open. There exists an epsilon positive such that C minus epsilon to C plus epsilon. C contains C and C minus epsilon to C plus epsilon is contained in D1. Now, AK belongs to for some K1. I mean, they're all generic numbers, not the same K1 that appeared earlier. and Bk also belongs to because Bk converges to C. Okay. Therefore, what do we have? So we have is contained in it. Okay, and Jk is contained in U alpha for every k k. What does it mean? That is U alpha is a cover for Jk with U alpha So what did we start with? We started with the assumption that Jk, but this contradicts assumption with no finite subcover. So what does it mean? It means which implies that is a open cover no finite subcover is false. That's a contradiction that you arrive at. So we have a contradiction that you arrive at here. This is false. That is, since the choice of u alpha is arbitrary, and this argument holds for all choice of open covers, it follows that J is that's a beautiful. So this is the Heine-Borel. So the Heine-Borel theorem actually proves that J is compact. Now we can see this. Okay, so we have seen that. So all bounded, closed, compact. Okay, so that is the final result. Okay, I think that completes the proof of the theorem, and it's a nice place to stop, and we explore this further. Our exploration has just started. Okay, now you can easily show that if a interval is, so I think I will make it. An interval is not compact either it is not closed or bound. The first case we have seen this. Bounded but not closed. And hence not compact. Similarly, minus infinity to plus infinity is closed but not bounded, and hence therefore we can conclude that compact if and only if is closed and this is the characterization of compact. This characterizes the compact that's the characterization. Okay. Now what we would like to explore is, can you go beyond this and say about compact, closed, bounded subsets of one, not just intervals, but beyond. We'll explore this. Okay, thank you very much.